Welcome back to Daily Dose of Space. Today, we're going to look at one of the most dramatic endings in the universe, the death of stars. And not just the general idea of a star explodes, but what actually happens inside a star in the final minutes, seconds, and even fractions of a second before it dies. When you zoom in close enough, the death of a star is one of the most violent and beautiful processes in nature. Temperatures climb into the billions of degrees. Atoms are ripped apart. Entire elements are forged in a violent flash. And inside the core, physics begins to operate on a timeline so fast and so extreme that even modern simulations struggle to follow it. Massive stars don't go quietly. They collapse, ignite, implode, explode, and leave behind the most extreme objects known: neutron stars and black holes. And today, we're going to walk through the full life and death cycle of these giants, all the way to the final fraction of a second when the core collapses and the star detonates. So, let's get started. Why mass matters: the secret of stellar life and death. To understand how a star dies, we have to start with something surprisingly simple: its mass. A star's entire life, how bright it is, how long it lives, and what it becomes at the end, is determined almost entirely by how massive it is. A star like our sun is relatively small. It burns gently, lives for billions of years, and dies in a calm, slow exhale. But a star 10, 20, or 30 times more massive burns so violently that it tears through its fuel in only a few million years. A tiny blink compared to the sun. The more massive the star, the hotter its core. And the hotter its core, the faster nuclear fusion runs. These stars fuse hydrogen into helium, helium into carbon, carbon into neon, neon into oxygen, oxygen into silicon, and finally, silicon into iron. Each step requires higher and higher temperatures. The star keeps going until it reaches something it can't burn: iron. And that's where the countdown to death begins. Iron, the element that kills star. Iron is unique. Unlike every element before it, fusing iron does not release energy. It consumes energy. That means once a massive star builds an iron core, fusion shuts down. And that's fatal. Fusion is the only thing that pushes outward and keeps gravity at bay. Without it, the star's core becomes an unsupported, unstable mass of iron. As the iron core grows, it becomes denser and hotter. It's being crushed by the weight of the star above it. A mountain of billions of trillions of tons of gas pressing down. The iron core eventually reaches a mass limit called the Chandrasekhar limit, around 1.4 times the mass of our sun. And when it hits that threshold, it collapses in less than 1 second. This moment is the beginning of the end. The collapse, a star's final half-second. Here's where things get truly extreme. Once the iron core reaches its limit, it collapses at a speed that defies comprehension. In the first 0.1 seconds of the collapse, gravity forces electrons and protons to combine into neutrons. This happens so violently that the core essentially transforms into one gigantic atomic nucleus, a neutron star core, in a fraction of a second. Temperatures rise above 100 billion degrees. The inner core shrinks from the size of Earth to the size of a city. The density becomes so great that a single teaspoon of this material would weigh as much as Mount Everest. But the collapse doesn't continue forever. Once the core becomes neutron dense, it stiffens. Gravity slams the rest of the star into this stiff core, and the star rebounds. This rebound is the beginning of the supernova explosion. The explosion, how a shockwave is born. When the collapsing material hits the newly formed neutron core, it rebounds outward in a shockwave. But here's the twist. that shockwave isn't strong enough to blow up the star on its own. If it were, supernovae would be simple. Instead, the shock stalls. It literally stops moving. For years, this confused astrophysicists. A stalled shockwave should mean the star doesn't explode. But we see supernova everywhere. The answer turned out to be neutrinos, tiny ghost-like particles produced in unimaginable numbers during the collapse. In the fraction of a second after the core collapses, the core emits more neutrinos than the Sun will emit in its entire 10 billion-year lifetime. Most of these neutrinos escape, but a small fraction interact with the material around the core, depositing energy into the stalled shockwave, re-energizing it and pushing it outward again. And this time, the shockwave wins. This interaction produces the supernova explosion, a massive detonation that releases more energy in a few seconds than the star emitted in its entire life. What supernovae really look like from the inside. A supernova is not a simple explosion. It's a chain of runaway physics. As the shockwave moves outward, it slams into layers of silicon, oxygen, neon, carbon, helium, and hydrogen. Each layer reacts differently. Some layers ignite again, producing a final burst of nuclear burning. Others are ripped apart instantly. The shockwave tears through the star at tens of thousands of kilometers per second, heating the outer layers to millions of degrees and hurling them into space. In the process, heavy elements like gold, uranium, and platinum are created. These elements are not made during the lifetime of the star. They're forged in the explosion itself. Every gold atom on Earth was once inside a dying star. And as the shockwave escapes, the star's outer layers are blasted into space, forming an expanding cloud of gas and dust, the supernova remnant. What remains? Neutron stars and black holes. After the explosion, the story continues with the core. If the original star had around 8 to 25 times the mass of the Sun, the core becomes a neutron star, an object so dense that a sugar cube would weigh as much as all the skyscrapers in Manhattan. Neutron stars spin rapidly, generating strong magnetic fields and sometimes producing beams of radiation, becoming pulsars. But if the star was massive enough, above roughly 20 to 25 solar masses, the core doesn't stop at neutron density. Gravity overwhelms even neutron pressure. The core collapses further and forms a black hole. The boundary between these two outcomes is still one of the big open questions in astrophysics. But generally speaking, the more massive the star, the more likely it ends its life as a black hole. The final seconds, a play-by-play of the star's death. Let's zoom even closer, breaking down the final moments of a massive star's life, moment by moment. 60 seconds before death. The iron core grows rapidly. Fusion stops. Gravity takes over. The star begins its terminal collapse. 1 second before death. The core collapses at 1/4 of the speed of light. Temperatures skyrocket. Protons and electrons merge into neutrons. 0.1 seconds before death. The inner core stiffens and rebounds. A shockwave forms, but immediately stalls. 0.01 seconds before. A tidal wave of neutrinos escapes from the core, passing through the outer layers. A tiny fraction deposit energy into the shockwave. The shockwave revives, accelerating outward with incredible power. 0 seconds, the explosion. The shockwave tears through the star. Nuclear reactions reignite. Heavy elements form. The star blows itself apart. In less than a second, the fate of the entire star is sealed. Supernova change the universe. Supernovae are not just fireworks. They're among the most important engines of cosmic evolution. They trigger the formation of new stars by compressing nearby gas clouds. They spread heavy elements across galaxies, enriching the universe. They create cosmic rays, shock waves, and magnetic turbulence. Without supernovae, planets like Earth would not exist, and neither would life. In a way, we are all made of the ashes of dying stars. Thanks for watching this deep dive into the death of massive stars. If you want more detailed, science-first videos like this one, remember to subscribe for your daily dose of space.